a loot, but all I got was the picture of the picture being made. But I guess that the loot's in the background. So okay, I guess that answers my question. This is why is safe search off? I don't know what that's about. Google's weird.
Inappropriate pictures
think
of
I've ever
loot.
seen that such uniformity in the Google search results.
Apparently, there's just a lot of different images, versions of this image around.
I think that's because the title of the painting or drawing is called Man Drawing a Lute. So if you search for that, you're just gonna get that particular painting
Yeah,
or drawing.
man playing a loop. No. Yeah, what I wanted was this. Ooh, this. That is an incredibly tedious way to draw a picture, but incredibly accurate. Anyways, so I guess we should get started. About that time. Um, yeah, we're talking about the camera model this week. Last week we did the rendering equation, but that's just like an abstract equation. Now we got to take cameras into account. But to take cameras into account, we got to have the pinhole camera model defined well enough to be usable. Um, it'll always be at the origin. It'll face in the negative z-axis. I can never remember if that means it's the scene is plus z. Is that right?
The scene is all in the negative sense, right?
Okay, yes, yeah, okay, facing along the z-axis, negative z-axis. So, um,
Yeah, yeah. Like instead, it's a right hand rule.
yeah. Um, Pinhole camera. Make a pinhole hole through something, and that we'll see the reflection, or not the reflection, the image of something. Uh, apparently, we assume things because it's easy or to do. This is an interesting qualification. I haven't read far enough ahead to know what it means, but we'll have to see what it means. Okay. Um, Light must be scattered or emitted from a surface for your eye to be able to detect it. All surfaces are scattering light at all times. The fact that we can see it is just because that those specific rays just happen to hit our eyes. Here it talks about the moon, and it's like the moon's reflecting light in all directions. So when you look at it, you just happen to be seeing the light that happened to be going in your direction. Um, the reason why we don't see images of the moon on every surface, because if the moon's image is everywhere, why can't we see it? It's because they all blend together. Um, and that's actually an insight as to why the pinhole camera has to be a pinhole instead of a big hole. So this describes making your own pinhole camera, uh, and it's kind of hard to follow in what I thought, but the gist is you have a box, you poke a hole through it on one side, and on like not the opposite side, but a different side, you poke another hole into it. Um, it doesn't say where, see? On the side opposite the white paper. Um, yeah, so the second hole is one for your eye to look through. Um, and you should be able to see a reverse image of you should be able to see a reverse image. Yeah, and that's all a camera is. Apparently that means room in Latin, camera does. That's interesting. Um, For an image to appear on the white paper, it must have passed through space before it entered the aperture. While we can't see the image outside of the aperture, a computer can simulate it. This is when we put the image for a plane in front of the aperture rather than behind it. And we do that because the math makes it simpler. However, it's a virtual image plane because it's not a real one. And so physicists like to differentiate it. Our goal is to sample the light passing through a point P on the virtual image plane in direction negative omega towards the center of projection, the aperture that I placed at the origin. In other words, compute this. Apparently you can do it by hand, and that's what I was looking up earlier. And this is Albrecht Dürer. He made a woodcut of him drawing a lute. And apparently that's like where this is a frame, there's a string, and the guy lines up the string with like the aperture point, and then his assistant or whatever closes the um panel and he draws a dot where he put the string. So it was a tedious process, but it could get a near perfect perspective projection um in 1525, which um yeah, the algorithm is the same, but with string canvas and wooden ink rather than code and computers. Uh, so a frame, canvas on a door. That's the word I was looking for. Um. Oh wow. Oh, that's interesting. There's more to it than just a string. Uh, okay. Yeah. Yeah. Note that this is the image plane in front of the center of projection. That's the virtual image rather than a real image, which would be upside down, generally speaking. Yeah, it's actually, well, rotated 180 degrees is actually, appearing inverted both horizontally and vertically. I guess that would be a 180-degree rotation. Yeah, okay. So on to the actual code stuff. We need scene data, apparently, and they have methods to, they being the abstractions that the book uses. Um, there's open asset import library, tiny obj loader. Okay. Data driven. Avoid hard coding the scene into your program. Yeah, that's a good idea because then you can render many things with one program. Okay. Measure incident light at each pixel. This is the heart of the render. The incoming light, Li p of omega, where p is the point in the center of the pixel on the image plane, and omega is the direction from the center projection through P. Real digital cameras estimate the incoming light? Oh, by averaging out a region. So we're going to be measuring points on a sensor rather than areas, whereas a real digital camera can really only do an area. It can't do perfect points because it, isn't infinitely small. And we have the aperture, which is the pinhole in our model. We have the real image plane, which for a camera would be this, but in our virtual image plane is ahead of the aperture, in front of, if you will.
Part of why
Um,
path tracer is so impractical is the fact that all those rays randomly bouncing, you just need such an incredible scale of them to get an up in the aperture, unless you're doing
yeah, yep. But
different way.
I've never heard of someone seriously trying to implement a forward path tracer.
Yeah, the 2D one that I'm doing is the only way it works is because it's really hacky, and the world only exists in a plane.
Find by raycasting the point X on the surface that scattered light towards P. I mean, he drew it here, so I guess that's our point X, but the incoming light was scattered or emitted from a point on some surface in the scene. So use raycasting to find that surface point. For shading purposes, we need not just X, but a small patch of the surface about X. Surface element circle in the way that a pixel is a small patch of a picture. Okay. Why are there why is there a lettered list? I guess it's just the measure of incident light at each pixel requires these steps. Okay. Switch from incoming to outgoing light. Once we have the circle visible through the pixel, we apply the relation light incoming equal at a point P is equal to light outgoing at a point X, the outgoing direction, with the outgoing direction being equal to the inverse of the incoming direction. It's basically saying these 2 points are equivalent. These 2 rays are equivalent. So we're now solving for L out of X of omega O. Okay, and then we can leverage the rendering equation. Okay, so what we covered last week, I think. Yeah, it was last week. The emitted radiance term in the rendering equation, LE, is a property of the circle and direction. Yeah, assume that we can query that directly. Or 0, yeah, that works too.
Got your camera pointed at a spherical cow.
Yeah. Um, Numerical estimate of its value. Okay. I see. So the assumption that was alluded to at the very beginning is that the only thing we're considering is direct illumination. The light illuminates a surface, and we look at the surface and its illumination by the light, and only that light and no other surfaces. So that makes sense. Okay. Once we've computed the radiance entering the pixel center, we'll store it in the corresponding pixel of the image. So effectively what it's saying is we trace a ray through the scene, and we see what surface it hits, and then we ask, okay, how bright is the surface from direct illumination, but from other from light emitting things for lack of a better term. And then we say, oh, well, okay, there's a light over here, and that happens to be the only light, so we'll only use this value, and then we'll just back propagate. We'll just basically say that's the amount of light that the pixel gets. So that's fun. So just dynamic range. Okay, so we'll use RGB, where we'll only have 3 discrete frequencies of light, red, blue, and green, rather than a continuous spectrum like in real life. And because computers store numbers in a limited format, we have to worry about storing too large and too small of numbers. So we're gonna deal with that. Talks about how we're actually gonna be able to see it. Glut. I didn't think I'd see that, but there it is. Glut is a tool framework from the 90s, a OpenGL framework from the 90s, and it's as old as the 90s, so use it at your own peril.
Yeah, it's been a while since I've heard that name.
Okay, so primary Glut.
Yeah, that's what I learned on
Yeah.
It's been a while.
I mean, for what it's worth, if you're just trying to draw pixels or just draw some stuff, it's not the end of the world to use Glut, but it leaves a lot to be desired, especially with compared to more recent OpenGL versions and frameworks meant for those versions. Yeah. So primary rays from a pinhole camera. Our renderer's camera will have a virtual image plane. Uh, fix the center projection at the origin. Y increases vertical and X increases horizontally, and Z points out of the screen. That's a pretty common. Is it wrong of me to assume that in computer graphics, Y being positive is a common convention? Y being vertical, I mean, not positive.
Play comment, but I've seen Z up decent amount as well.
I know Blender uses Z up, but um
In world space, yeah, Z up is pretty common, but I think when you're talking about the image, I think Y up is pretty common.
yeah. Yeah, I think that I've always done Y up, but that might just be because I'm used to Y up for the image. You know, X, Y is the two coordinate axes of the image that matter the most, and then the Z is an optional one. There's like a chart of the 4 or 5 different common orientations: right-handed, left-handed, Z, up, down, left, right. All sorts of fun things. And all like the major graphics APIs do something slightly different, and it's very fun. Yeah, Z up is math. Yeah, I think Z up being common among mathematicians is common because it makes sense if X and Y are your two input axes and Z is your output. And so you have two input axes on the horizontal and one vertical output. Um, okay. Hey, got the dolphin. Oh yeah, it's that image I was thinking of. Literally that image. Um, I'll just click on it because then everyone can see it
The
for sure.
alignment chart.
Yeah. Yeah, we need like a alignment chart, but instead of left-handed, right-handed, it's like the evil, chaos, neutral, lawful, good, all that. And then we put all these different tools in them. But yes. So Unreal is Z up and left-handed. It's like all on its own. Jeez. 3ds Max and Maya are like made by the same company, aren't they? It feels weird that they're different, but see like Autodesk, AutoCAD, there's 3ds Max. Whatever, I'm just gonna get annoyed if I keep looking at it for too long. Um, okay. Okay, so we have some sort of angle theta as a parameter for our direction in our image plane. Ah, Um, fixing the vertical field of view. Okay. Um, I think I skipped this part. I should have read this part. Image plane B, the plane at Z near negative number. Okay, anything that's too close to the image plane will not be seen. That's why it's the near one, because if it's too near. Well, um, yeah. So our near plane will be very close to, but not at the origin. This is a side view of a pinhole camera. Um, oh, this is So the theta is describing the field of view, and it's like the field of view is just on a given axis, how much of the scene can you see in terms of an arc? And the top of the image measured to the bottom of the image, and you basically just measure that angle as if it was in real world coordinates, rather than a image, which is a flat plane. And so here we have, this theta angle, that's our field of view, and it's and so we're the parametrizing the field of view based on the vertical axis, and then the horizontal will vary based on the TV or computer monitor's width, which is a very sensible, approach when you don't get to say exactly how wide the TV or computer monitor is. So some people have ultra wide monitors that are like 5 times wider than they are tall, so that's fun. And also it's saying that the vertical field of view determines how much horizontally we get to see, but the width of the output image is how much of the horizontal. Did I say horizontal? I meant vertical. How much of the horizontal we get to see of the thing, whatever. Oh, top right, top left corner is the 0, 0. So here we have a perspective projection kind of off axis, whereas here we have a orthographic screen space view where it's just there is no perspective view. It's all just parallel lines are parallel. Do they talk about orthographic views at all? No. Okay. So pinhole camera class, we got a z-near variable and a field of view variable. So this will be a angle, this will be a distance from the origin to the image plane, the virtual image plane. We need to do a raycast, so we have to have some sort of casting algorithm. Here we have get primary ray. We take an x and a y, a width and a height, and so that is our width and height of the image. And what does the x and y represent?
That the pixel that you're trying to figure out?
Yeah. Pick. Okay. Oh, is point P an output parameter?
Oh, probably.
Yeah, it is. Okay, that's what was confusing me. So we have, yeah, the pixel coordinate. Um, are they a proportion between 0 and 1? No, they're an absolute, like, 455. And then we'll divide it by our width to get the proportion between 0 and 1. And then subtract it by 0.05 to make it a value between negative 0.5 and 0.5. Wait. No, that's right. Yeah. Because even though our image, is centered around 0, 0 in terms of pixel coordinates, the center of projection is centered in the center of the image. So we need to translate our pixel coordinates into origin. Yeah. So like x of point of if our image height was if our image width was 800 pixels and we were wanting to calculate the 400th pixel horizontally, and then what this does is divide by the width, which is 800, so that'd be 400 divided by 800, which is 0.5, and then we subtract 0.5 from it to get 0 because we want the very center. Yeah. 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 Let's compute the side of the square at z negative 1. Okay. So this is the funky math to do to get the side of the square based on our field of view, and you can do the trigonometry to figure out that you need to take the tangent of the angle divided by a half, because our why is it a half? Whatever.
Doing a tan for every primary ray.
Yeah. This is
Ho-
not meant to
Hopefully
be
your
performance.
compiler is smart enough to constant fold that. Or I guess it can't be, right?
Nope. Generally, it couldn't. It
Unless it was const in the original structure or something, but no.
I mean, I can believe a compiler being smart enough to constant fold it out. However, knowing the liabilities of the language of C++, I wouldn't, and C, I wouldn't be surprised if compilers generally couldn't do that. Just because of the they
Yeah.
they'd have to be able to know that that variable value won't be changing.
Yeah, yeah.
So it'd have to go, yes, this is set here, and there's no access to this outside of this scope or whatever. And every time we call get primary ray, it never changes inside of it. So we can just, you know, static, turn it into a single function at the top. But we're getting into compiler theory, not graphics theory. So by discussing that in too deep of detail. Yeah, not making the screen size hard-coded is nice. Definitely recommend. Oh, so this is there's an implicit coordinate transformation going on here. Implicit. Because our screen image is negative y, whereas our global, like our world coordinate system is y positive. We have to invert the y to go from this to this. Oh, now we get radiance? I'm not radiance, dynamic range. Display must reconstruct the radiance function from the samples, and then integrate over that reconstruction to emit proper power at each display pixel. That is an incredibly dense way to say it must turn pixel brighter or not as bright.
Yeah.
So,
Yeah,
like,
I think it has a lot to do with anti-aliasing, right? Like and you might have sampled at a different frequency than the screen pixel frequency, right? For example.
yes. Yes, that is a yeah. There definitely is the sampling issue in terms of the area, but I think it also is referring to the I think it's really referring to the brightness here, because I mean this is talking about dynamic range. So, I mean, I guess yeah, if your image isn't it isn't pixel aligned, then you would need to have some sort of, I guess, anti-aliasing to make the image not be jagged and smooth on the monitor. Um, uh, yeah, computer monitors aren't great, and you have to pay a lot of money to get ones that are better than not great.
It's still common to have a 6-bit per pixel.
Yeah, 6-bit with dithering
Huh.
is actually not uncommon at all.
Didn't know that.
Like 6-bit.
I saw something not that long ago. It was 16-bit
wonder if like modern monitors that use LCD are actually
There are some
bit.
that are 10-bit now. Some
Yeah.
consumer stuff is 10-bit.
Yeah, there's lots of people who talk about it online. Spend hours. I accept. No, I don't accept. Okay. Except human eyes are really, really good at seeing things. So take an image with correct ring and you know what? I think this is actually just saying that, you know, you can create an image, but that doesn't mean it has the right brightness and contrast. That's, I think, pretty much all it's saying. Maybe tone is the better word for it, but I think it's saying computer monitors have to figure out how bright things should be, and we have to make sure the input to that brightness function is correct. In addition to the computer monitor knowing what correct is and displaying it correctly. Yeah, gamma encoding. So there's a lot of human senses. I think like sound is also logarithmically sensitive, where a loud sound is actually like 10 times 10 times louder than a quiet sound. Maybe not 10 times, but um, is that just called Weber's law? I'm gonna look that up. Oh, yeah. Human perception. Yeah, we can perceive changes that are only relative to the quantity being changed, where these two images have the same absolute change of dots between them, but the 10 to 20 is, we can tell the difference, whereas 110 to 120, we're like, they look the same. They look very similar, even if, you know, they're not. So it's probably the law to use. Yeah, the perceived brightness between 1 watt, 10 watt, and 100 watt are this, or yeah, the difference between 1 watt and 10 watt is the same as 10 watt and 100 watt in terms of perceptual difference. Yeah, our eyes are very good at adjusting to bright and dark, and why you shouldn't just stare into the sun is because it'll burn your eyes out. But if you are standing outside for a long time, your eyes adjust and don't let much light in, and so it doesn't look that bright after a while, even if it is really, really bright. Hundreds of gradations in intensity. Log of x and x of k have similar shapes. Can we go to Desmos? Because I just don't. I'm trying. So we have x to the k. And what was the other one? Log of. Oh. Oh yeah, look at that. Let's go to 0 and 1. So like the k of 0.5 looks like the logarithm just downshifted a bit. Of course, once you get to 1, it just turns into a flat line. Same with 0. Oh, okay. And x less than 0. Wait. Oh, x is greater than 0. I read that backwards. I'm dumb. Yeah. Yeah, we got 8 bits. We use the 8-bit per color channel standard. Mapped to a linear scale with radiant slope k and black level offset 0. Yeah. So effectively, if we only have 256 numbers or values to store the brightness, and we use a linear curve, then there isn't that much precision because we can't perceive the things when all the precision goes into values that look similar to us. Yeah, it will look indistinguishable. And yeah. Oh yeah, so like if we flatten out this, we compare the things when we have a linear response, the change over here is very apparent, but the change near 1 is not apparent. But if we use I guess a logarithmic curve, then the value changes are much more readily apparent. Yeah, it's hard to describe verbally. Gamma encoding, when we go from a linear algorithm to I guess, exponential one. Yeah. Yeah, so the value we want to store in the pixel is going to be the L. What is L0? Oh, we just assume L0 is 0 watts. Yay, assumptions. We divide the luminance by the gamma factor. No, not gamma factor. What was K?
The intensity slope.
That's okay.
This actually explains so much, though. The paragraph, we don't know the intensity slope k, but we can set it empirically. In other words, display the image and adjust k until the brightest areas are only slightly overexposed. So that's what's happening every time you play a new game, and it makes you mess around with the sliders.
Oh my God, goodness, you're so right. Um, so we're like, hey, we don't know what your monitor looks like, but to make sure that it looks good, adjust these sliders until they look like this thing we're saying it should look like. And then boom, magic. Yeah. Okay, yeah. It's a rabbit hole, gamma encoding, and the logarithmic nature of light or perception of light. So that's a rabbit hole. And 2.2 is our magic number. But this one lets us figure out the correct thing for the monitor and just use an omega that gamma that makes sense. Oh, I got a link for advanced things, so I won't look through it now. But
It's about designing a tone mapper, and it talks about
this
our
is a
perception and
2005. Wait, no,
monitors.
it's not. This says 2005, and then the slides say 2016. I'm sorry for just interrupting you.
Basically, it's just something that you could look at later.
Yeah. Okay. um. So because 1 is the highest value we have, if something is too bright, it'll just clip and make everything white, and you won't have any, like brightness there or any contrast there. And at the same time, it won't look as bright because the monitor can't get that bright. It can't actually simulate a super bright light because that would burn a hole in the monitor due to the power usage. Well, maybe that's a bit hyperbolic, but bloom, we just fake it with bloom. We make bright areas bleed their light into surrounding pixels, and it looks right because somehow that's what light actually kind of does. Very bright lights do that, so it's great. We take the original image, we blur it a bunch, and then we add it back to it, and so now we get a blurred image. Blurring is also something you can spend a lot of time in and develop very sophisticated techniques for. Whoa, what's this talking about? Oh, maximum pix. Oh, is that what desaturate? Oh, yeah. Yeah, yeah. So if we try to make things more saturated, which means make the pixel values increase uniformly, then it just turns to mush because yeah. Uh uh yeah, apparently if it's really bright it looks white, and so rather than just desaturating it by turning everything white, we just make it more white, I guess. Um
I think it's to avoid the like greens and yellows.
okay. Yeah, because yeah, this the stick and the grass and whatever and the moss have all turned everything yellow and green when the original image was much less yellow and green. It was yeah, and then this is all the code for that. In one function, we have we adjust stuff, do math. This is just for the and gamma correct. Okay. This is the gamma encoding where we divide the luminosity by our gamma, or we take our luminosity to 1 over the gamma power. And our L is K, which we found by having our user slide sliders until the image looks white. We want to get the maximum radiance of any of our frequencies, and we divide our input by that. So we normalize it. Oh, is this?
All the desaturation.
Okay, yeah. Oh, it's correcting for basically it's correcting for this image. It's finding the brightest channel and then dividing it so it's all normalized. And then we restore the magnitude, but fade towards white when maximum value approaches 1. Okay. That makes sense as to why we're doing that. Okay. And that's the end of the chapter. What? Oh, yeah, okay. So apparently the restoring magnitude but fading towards white is the lightsaber effect. So
Wait,
do we want to
Wait,
look at
why?
that? What?
Why does the so it says the bloom will have the original hue, but oh, is it just because you're not doing this desaturation on the bloom pass?
I think so.
As the intensity becomes larger, it has a tendency to desaturate. I've heard that other places. I'm not sure what the logic is there.
Wish there was like a link or something. Pixel's not a little square. We've read that paper, and it was interesting.
Yeah, I think that's a good paper.
Yeah. All the units and symbols. Yeah. So variable dynamic range, tone mapping. So, do we have anything more to say about our pinhole camera model, or is that it?
Hoping for a refresher on the perspective matrix, but I should just do that myself.
That may be a separate chapter. I'm gonna look at the contents index. So we now we can do raycasting next chapter. I don't think. I wish I could
And I
build
guess there
now.
is no projective. I mean, since we're doing ray tracing or ray casting, there's no projective matrix.
Yeah, I guess no need to.
It's sort of implicit in the, picking the point in the ray direction.
Yeah, it just falls out.
A little bit gentler introduction when you don't have to deal with the matrices.
Fair.
Oh, you don't want to deal with 4D numbers?
Speaking of pinhole cameras, we could talk about not pinhole cameras, like how you get depth of field by expanding the aperture and the focal length and whatever. But I don't know if that's talked about in
I'm
this
looking at.
site.
I'm trying to see if it is, and I don't see it. Hail of Two Cities. I'm sorry, that title stuck out at me. What is it talking about? Oh, okay. It's completely. I doubt it. Because that's going to be dealing with the surfaces themselves. You know, what light goes into a surface, what light gets scattered around inside it, what lights go out. Um, is there a, I mean, does, do we want to look at the ray tracing on weekend? Because I know it has some stuff on depth of field and blurs and stuff. Motion blur, I should say.
Yeah, so he actually has in the, I think, path tracing, there's the camera intervals, which is probably what you're talking about.
There's a short section in the ray tracing on one weekend about the thin lens model.
Do you know which book or chapter it is?
It's in the first one. Not too far from the end of the first book, I think.
Have
Oh, I think ray tracing in one weekend. Oh no, maybe a Scratch a Pixel had something about depth of field. Actually, I can find that.
Scratch a Pixel. I always thought it was Scratch Pixel. Oh my God, what? Is that like a recent change, or have I just never seen that A in the middle there?
I think it's a new Mandela effect.
Oh God.
I think it's always been.
I don't know what to trust anymore. Um, skip the math. Acceleration, light transport, geometry, digital imaging. No, this is. Where'd all their like Oh, rasterization. There's other rasterization. I don't see anything about lenses here, but maybe I'm just missing it.
Yeah, I'm trying to look it up too, and I'm failing to find it.
Yeah, no, I don't see it here. I don't see anything that pops out at me. I want to see this thing people are making fun of. I mean, oh yeah, PBR book. Yeah.
Yeah, I want to do realistic lens models at some point. That's such cool shit. The like refractive
Yeah,
optics
I
with
know.
multiple indices of refraction.
Um, uh, thick lens approximation. I feel like that's an insult, a thinly veiled insult. Like, people with thick glasses.
Like it's as opposed to the
It's
thick
really not.
glasses approximation.
Yeah. Um, oh, okay, I'm starting to see equation. Starting to see equations. The
Triggers
exit
equation.
pupil. Boy. Um, yeah. The rabbit hole goes deep when you want to accurately model camera lenses and not just have a pinhole for everything.
Yeah, I saw somebody on Twitter that was doing this a while back. Um, yeah, they were doing like specific physical lenses, like based on I don't know. They had some way to like represent. They had some file type that represented the shape, the geometry of the lens elements.
Yeah. Mm,
I was playing with something
yeah.
last week that was a spherical camera model. It was kind of cool.
You want to showcase it? Or is there anything to show?
I have a couple of pictures. I actually messed around with it